But now for this talk, please go.
Okay. Okay, thanks for the opportunity to give the talk at this workshop. So I'm going to be discussing about how to do DIS on nuclei using holography. So this work is based on these two papers with Ismail Zaid at Stony Brook. So first I'll give motivation for this work. And this work basically is going to be, so this talk is going to be divided basically into two parts. So the first is I'm going to look at DIS on a dilute nuclei, and the second one is DIS on a very dense nuclei. So the first one will correspond to for large X region, and the second one is going to be useful for very small X region. And finally, summarize and conclude. So the motivation is clear, right? So the EMC collaboration and others at CERN and SLAC have made a surprising observation that the structure function of iron in nuclei is substantially different from a deuteron. So the question is, why would scattering at high energy and momentum transfer at the DIS region should affect should be affected by the binding energy, which is very small compared to the DIS energy scale. So in this work, we are going to examine the role of strong coupling when nuclear many-body system is produced probed electromagnetically in the DIS limit. So for the first part, for the dilute nuclei with small atomic number, so we are going to consider leading contribution from one nucleon state smeared by its Fermi motion. So that means we are going to do DIS on each nucleon, but which are undergoing a Fermi motion. So this, as we will see later, will be justified in large X region. So we are going to estimate this DIS scattering on the few nucleons amplitude using holography. So we have nucleons which are undergoing some Fermi motion. So we are going to scatter on each nucleon, and the structure function for each nucleon we are going to use from holography from the strong coupling calculation by Polchinski and Strassler, and we integrate over their Fermi motion, and that defines the large X region for the DIS.
So then there is no A dependence?
There is A dependence, it's going to show.
And it comes through the Fermi
function? So in the Fermi function, also for the distribution, we are going to assume Thomas Fermi approximation for the Fermion distribution. For that, we'll introduce A into the setup. So this is the first part. So for the second part, shadowing, for example, in the small X regime is currently understood as a current scattering on two or more nucleons in the nuclei, as opposed to incurrent scattering for individual nucleus. So for the first part, we are looking at incurrent scattering on each individual nucleon. But in this small X region, we are going to be looking at current scattering where there is some correlation between each nucleon. So in this region, we take this current scattering to the extreme, and we are going to say, okay, this nuclei from holographic point of view, we can represent it by extremal RNA ADS black hole. So that will be equivalent to scattering on this extremal RNA ADS black. So we'll discuss that on the second part in more detail. So this is what I said right now. So for the first part, for the dilute nuclei, we are going to consider deep elastic scattering on a nucleus described by this density expansion. So this is the momentum of the nuclei. We are going to put it in the stress frame. So the leading order contribution is what we are going to compute. So the other contributions are coming from correlation between or interaction between the nucleons, which we are going to ignore. But when we take this to extreme, then at the other end, we are going to have excimal RNA ADS black holes and their quantum fluctuation.
Sorry, what does G mean?
So G mu is just the current correlator for each nucleon state. Okay. And this is current correlator for on the whole nuclei.
2n means a 2 nucleon state.
Yes, yes. So we have a current correlator on each nucleon state, and for higher for manifold systems we will have more nucleon states. So this is how we are going to take the phase space to be.
And you take in a retarded green function because that's what you know how to calculate.
Yeah, actually for the vacuum we are for the vacuum case we can calculate time order JJ correlator directly. No.
Well, but not interested in vacuums.
Yeah, but this one. So we're looking at we're going to look at scattering on each nucleon and integrate over its Fermi motion. So for each nucleon, the structure function we are extracting is on the vacuum.
Oh, so each nucleon has to interact. That's why you have a connector.
Yeah. That's why we have this. But at leading order, we have just considered on each nucleon, but distributed by Thomas Fermi approximation. So for each nucleon, it's just from holographic point of view, it's just opportunistic Strassler, where scattering on each nucleon.
So sorry,
that means,
you have to understand. When you have two nucleons,
yeah,
we interact with both of
them. We are ignoring the interaction between them.
Yeah, between them, forget it, right?
Yeah.
But the interaction, the current correlator, which couples what your Maxwell field, right?
Yeah.
The mu field.
Yeah.
The same mu field will talk to the nucleons, to both nucleons, right?
Yeah.
Okay.
So that means basically for each nucleon, we are looking at deep virtual Compton scattering. So okay, it's just more detail. So this is the structure function for each nucleon, and this x is when the nucleon is at rest. But now we are considering its Fermi motion. So for the Bjorkan x for when it's undergoing some arbitrary motion is given by this. So as I said, calculating this is basically it boils down to computing these diagrams in ADS. So this is just deep virtual Compton scattering. So this is the ADS boundary. So once we calculate this, we'll take imaginary part of this in the forward limit. That from that we can extract the structure functions for the each nucleon.
What is a nucleon?
So the nucleon for us is just a fermionic state. It's just a fermionic. It's a dilatino. It's a fermionic state in the bulk. So we are going to this. So in the DIS we have virtual photon coming here. Then that will turn into some resonance here, just like vector meson model. So this resonance scatter with this proton state. Then this is where we're integrating over this final state. So the imaginary part of this in the forward limit, from that we can extract the structure function for this proton.
So and what happens if you have two protons?
Well, in the initial state, then you will have more correlation between them.
The rest of the correlations only come because of your Fermi motion.
Yeah.
And what does the diagram look like? I thought you said they interact with both.
No, here we are just looking at scattering on each nucleon,
right?
Which is only undergoing after
the matrix element with two nucleons.
For two nucleons, we are not looking at that in this work. We are just looking at the leading order.
First term.
Only the first term, yes.
Oh, so you don't care about that?
Yeah,
I see.
We're only looking at this part.
Yeah. But is there any double counting in this expansion, saying that two nucleon part includes individual one nucleon, one nucleon? Is there double counting in the expression?
I think that's why he requires them connected.
Yeah, connected.
He wants them to interact with both. I don't even understand what diagram it is.
Exactly, I was just thinking about that one.
I'm not sure I understand it, but the words which are being said is you interact with connected parts.
Subtract.
Yeah.
Connected, yes, subtracting part.
Yeah.
And what was sorry, Could you go back one slide? I just don't understand the formula at the top. Why is it two terms? No. Please. Yeah. Where
Yeah,
does
yeah,
this
yeah.
come from?
Okay, so that's good. So we have two terms because for the Thomas-Fermi approximation, this is the radius of the nuclei. So below, in the bulk of the nuclei, this is given by, we are taking the density to be constant. And on the surface, we have some distribution. So that's why we have, this is on the surface and this is the bulk.
R8, R8 plus delta.
No,
Yeah.
I kind of noticed that you know what to make.
Yeah, okay.
Now I see. And delta is a free parameter.
Yeah. It's the techniques. So this is the deep virtual computer scattering. So this imaginary part of this gives us the structure function for the proton in the large X region. Now for small x, one also compute the T-channel graviton exchange, and this is the current correlator by the graviton exchange, and the imaginary part of this corresponds to small x region. And all the calculation I just showed in these two diagrams, both S-channel and T-channel, are in the point particle limit, but we are looking at an effective type 2B supergravity interactions here. But but these objects, in principle, they have to be strings. We are looking at alpha prime goes to 0 limit or the point particle limit. So otherwise, you can think of this as exchange of closed strings.
That's what you're just saying. If you exchange a graviton, it will be real. There will be no imaginary parts. So to cut it, you need to put a closed string there.
No, this one at leading order has imaginary part.
Graviton?
Yeah, it's 1 over. So this gives you 1 over x squared. Then all the corrections are 1 over lambda corrections.
But gravity is real. I mean, metric is real. Where is it?
No, it's not the metric. It's just the exchange here. You have Feynman propagator here for the group.
What? Or?
You have Feynman propagator here,
Yeah.
and it has resonances. So when you cut it and when you sum over resonance, that's give you imaginary part. The same here. There is no difference from here. Computer scattering.
It's always string. It's always a string. It's not
Yeah.
graviton.
No.
Look at that, Doctor. You have this Pomeron.
Yeah, but it doesn't have to be Pomeron. So the point particle limit already. Where did I go? So this diagram, even in the point particle limit, you have bulk to boundary propagator. This bulk to boundary propagator is a Feynman propagator with minus I. Then when you take the imaginary part, you replace it by the delta function. Then these are resonances, so you sum over those resonances. That's how you get the imaginary part.
You see,
This is basically
right.
the amplitude scale. That's how opportunity and strategy.
Right, so this is all very well, but if you go to the other diagram, you cannot put a graviton on mass shell.
No, you're not putting anything on mass shell.
No,
This is virtual graviton. You have bulk to boundary propagator for the graviton. You have minus I. Yeah, this is bulk to bulk propagator.
So this is bulk. Okay.
Yeah, so this is bulk to bulk propagator for the graviton, and these are just bulk to boundary. These are normalized states. So this is our this is bulk to boundary propagator because you have operator insertion here. So this is bulk to bulk propagator, and it's a Feynman propagator. This has minus I prescription.
Right. So if you start taking imaginary part this way, you put it on mass shell.
Yeah, and there are resonance. You sum over those.
Then it's going to be 0, right? Because you have a nucleon come in, emit a massless sunshine particle, and recoil to a massless nucleon. That's prohibited by energy momentum conservation, even in ADS.
Yeah. No, this is just a normal propagator.
Yeah. So if you cut it, the
Then you get-
process on the left of the cut,
You get delta function, right? The imaginary part corresponds to the delta function.
of like very collinear splitting.
I guess this kinematic is 5 dimensions, so there's the third dimension, which produces
Resonance.
Three-dimensionality. Why does it mean?
also maybe you're thinking of in terms of 4-dimensional momentum, but it's extra 4-dimensional. Its wave function has spreading. So there are resonances.
In fact, there are virtualities.
As a kind of
They're not on shell. The fifth dimension corresponds to virtuality.
yeah, but I think the spectral density should be sharply picked at this mesh one share.
Yeah.
So you get just discrete delta functions.
Yes,
Instead of smooth.
Yeah.
Wait, where does this start from? Yeah. some excitations.
So
Graviton itself wouldn't have it. There's no black hole here. So there's something releases it.
yes, so imagine you have a field in a complex space, say one dimension. There is a excitation spectrum. Just
Right. So what is compact here?
this extra dimension. This
Reduced dimension. Why is it compact?
So I think he's considering
So,
defining geometry.
Yeah.
Right.
So,
So that's what I'm saying. You have to cut off.
Yes.
yeah, you can introduce in the hardware model, you can gap the resonances, but for the safety, there will be continuous spectrums.
Okay.
So instead of summing over this resonance, you integrate over each. So the only difference
between
between this
infrared cutoff. You had no infrared cutoff.
infrared cutoff, then that will gap the resonances.
What?
The resonance will be gapped.
Yeah.
So these are just global resonances. It's not a graviton. It's ball-to-boundary propagator.
So if you had no cutoff, would you still have any dimension?
Yes. Because this propagator is just a massive Feynman propagator. For each globus, you have mass. So the propagator is like this.
What would the mass be?
Yes, so maybe
Proportional to it, there is no cutoff.
without any confining gap, I guess you could say
You have
not risking 5-dimensional momentum to surface mass in terms of 4-dimensional vector. Imagine E square is P 4-dimensional.
so this is Z and Z prime. This is our propagator.
Momentum along Z direction
But-
can surface mass.
But it's possible. You mean it's not conserved, right? Could you take something that writes better?
Yellow.
Very likely.
How do you clean that?
The razor will be on the right. Mark might close it.
This is even more now.
I think
Black one is
yeah,
here.
black one is probably. Of course, a lot of gaps.
I can tell. So this is, for example, this is a propagator, bulk-to-bulk propagator. So it's given by, for the safety, it's going to be integration over all resonances. So this will have some integral representation. It's given by d omega squared over 2. And you have a wave function for each state. So this is the propagator.
Next square.
Yeah. So up to this resummation, this is nothing but just Feynman propagator on flat space. The only difference is now we're integrating over each resonances. For the safety, there are no gap. If it was if you introduce infrared cutoff and if you gap it, then it will be a sum over this each guys.
K squared is which metric is
Sorry?
gravity metric, right? So K squared is minus K0 squared plus K vector squared, right?
Yeah.
Okay. So the omega squared is virtuality. It's not on shell. It's virtual.
Yeah. It's just integral representation of this.
So Yuri, to answer your question, all of that doesn't represent on shell vector is 4-dimension. It represents off shell vector. Time
I
like.
understand the statement. I just
That's
wasn't-
electric.
like my old memory of Kolchinsky and Strasberg was that they needed to put the actual string exchange to get the imaginary part. And somehow you're telling us now that they didn't.
That's the correction. The stringy correction.
No, that's a voice, that's a formula.
Yeah.
But they have GIS, a large jet, they have GIS at 3 level.
Because of that.
Yeah.
So we're cutting this.
There is an exchange of hadrons.
Yeah, it's exchange of hadrons, exactly. So they have this. So this is basically when you cut it, this is what you get.
Okay.
That's it. And the propagator cells have this form. So they are exchange of this fermionic resonances. That's what gives you the image.
But that implies a specific final state, right?
Yeah.
The final state is you cut graviton.
Yeah, graviton.
What translates into on the boundary. But,
yeah. So there is no difference between graviton or scalar field. I mean, technically, all bulk-to-boundary propagator have this form.
No, that I remember. But I mean,
so then the structure function, for example, is going to be like, for the graviton exchange will be 1 over x 1 minus sum with 1 over lambda correction. So in the infinite coupling limit, this is what you get.
Right, but even to
so the string correction comes, the 1 over lambda correction comes from by exchanging strings.
Yeah.
So in the point particle limit, you just get this. So, but if you say, okay, let's do string exchange, then you are looking at 1 over lambda.
But I don't remember it this way. I remember that if you just exchange gravitons, which you can do using just general relativity, you don't have to write any property, right? You have a source, which is your proton, it emits your graviton, and then your emil field fills that source. That thing has no imaginary part.
No, it has.
And then to get that imaginary part, they have to do something. I don't see it was that.
Exchange two gravitons.
No. Yeah, 2 would be wrong because then you get x squared.
Yeah.
It was 1 graviton, and the imaginary part was coming from something like smearing it and then taking the imaginary part. And then
what they do is you can read some more.
What?
I don't remember what was our level amplitude.
I remember everybody paper was Yoshi and Toby Bo, and then they actually had to do the thing. And you were looking for 1 over long ago.
So what you're saying is the resummation. You need iconic resummation.
I just kind of don't believe this picture because you see the graviton is a pomeron. It's clear you cut the pomeron, you produce particles. This is a multi-peripheral model.
Yeah.
If you cut it like you draw a cylinder and you cut through it, you produce a ton of particle covering the whole repeat interval. And you try to like cut it like a Christmas tree. And that doesn't look.
No, this is very rigorous mathematical rigorous thing. So this is Witten diagram. You know how to compute
okay,
them.
fine. You can use me. I'll go and get my laptop. Look up Polchinski's Rasa
Yeah,
That's what I'm doing now.
Are you doing it now?
Yes.
I can stay. I was going to get some exercise.
Yeah.
I found it.
I don't remember already, but yeah, the years ago, right?
No,
This
this one,
was
the long
stress
one.
here.
That's
What's
the
the
top one.
affiliation of stress?
There's no affiliation.
You should put the long one.
Yeah.
That you have.
Right.
That's not the one I see short.
Well, okay, please carry on.
I don't find it.
If it all turns out to be wrong, then
No, trust me, it's not wrong. So this is what you're talking about. So this is for the large X, the S channel diagram I show you. For the graviton exchange, you have this alpha, this exponent. As I told you, it will have some correction from the stringy correction, and you can also resum the graviton exchange. You get some iconine form, so you will have more correction to this. But they are all 1 over NC
this
suppressed.
is already a sum of small x and large x.
This is small x from S channel, and this for large X for each nucleon.
Large x, if I'm not
No,
wrong.
large X and small x. Yeah. Okay, so
This is a result of
this is Polchinski.
your diagram or
Yeah. So this one comes from the S channel.
SS.
Yeah. A cut of this will give you this. So this one in the infinite coupling limit give you this exponent will be just 1. That's just from the resonance. Then if you have stringy corrections, then you'll get 1 over lambda correction. Okay, so this is for DIS on each nucleon. So now we are going to integrate over this Fermi motion using the formalism I showed you earlier. So this is how the structure functions look like. This one is for strong coupling. This one is another part of parameterization for the weak coupling. So we're interested in the R ratio. That means we are going to consider, we are going to look at the ratio between the, since we are interested only in the large X limit, we are going to put C to 0. That means we ignore the gravitational exchange, and we just look at the large X region. And for this large X, so we'll take the R ratio between the one integrated over the Fermi motion divided by the just scattering on each nucleon, given by this. And the R ratio looks like this. So these parameterized curves are for the experimental data parameterized by this curve, and the solid lines, the solid lines are our results for different A.
So this is why you parameterize the data instead of just plotting.
Yeah, this is a parameterized
Why
one.
don't you just plot the data?
Yeah, actually,
The bars?
this was much easier to do this.
I'm sorry, what is the R ratio? Could you define it?
The ratio is basically the ratio between the structure functions for
You're welcome.
So the R ratio is just the structure function for the nucleon divided by A times the structure function for the nuclei divided by proton.
Usually,
Yes.
Shadow.
So yeah. Oh. Okay, so in for large X region, so it looks like all this enhancement is described by the Fermi motion.
Oh, so it seems like your trend is opposite on the data.
No, it's got the EMC effect there.
No, but you see, if as A increases, it goes from blue to red.
Yeah.
And the data goes from blue to red the other way, right?
Yeah,
Oh, you're right.
the A dependence has
So
some.
the X shape looks
Yeah. And we don't know why that changed.
well, that's not good.
But
Yeah,
you say this is the empirical ratio. Yeah, the empirical ratio is going the other way. Yes.
Yeah.
So what's causing in your case? What's causing the EMC effect?
It's purely due to the Fermi motion.
But that's not true I mean, that's not a standard nuclear physics explanation. Fermi motion won't give you an EMC effect.
Yeah, but so in this model, we just looked at the nucleons by Thomas Fermi approximation. They are just, so we're looking at the Fermi gas, which is under some binding potential, and we're scattering on each. So then we are scattering on each nucleon and integrated over their Fermi motion, and we have included the binding energy.
Fermi motion gives anti-shadow.
Well, the part of very large X, that's certainly Fermi motion.
Yeah.
But traditionally, the EMC effect, to my knowledge, no one has ever tried to explain that by Fermi motion.
Yeah, but
But you're somehow saying this is coming out from Fermi motion, and you're just.
and also we are using the structure function for strong coupling.
Okay, then I should rephrase my question. What in the structure function for strong coupling allows you to get the EMC effect?
I mean, physically,
It's
just that's how.
yeah. I mean, because the EMC effect here is what, a 30-year effect, and
What's the NC effect?
it's a dip at x equals about 0.7 to 8.
Yeah.
Right. Well, the small x, that's the anti-shadowing associated with the conservation law. That the EMC effect forces you to have an anti-shadowing effect at small x.
But also, like, if your A goes to 1, what happens to your curve? You go to 1 because, again, like,
Since the ratio is better.
Right, but the trend at the moment, at least for these two values of A, is like the larger the nucleus, the closer to 1. Well, at least in the region of this plot, it gets closer to 1. Yes, okay. But it's not going to monotonically approach one, I see.
No, monotonic for sure.
Yeah.
Walk around. Yes,
Yeah, the A dependence needs more understanding. Yeah. But the fact that it has this quantity feature by itself is interesting.
Are the dotted curve experimental?
Yeah, yeah. The dot curves are parameterized experimental. Okay, so this is for dilute nuclei. This is what we have. So we'll go to the dense nuclei. So so here we are going to look at DIS on black holes. So this was first DIS on thermal black hole was initiated by Hatta and Yanko and Muller here. So what they did here was that they were looking at deep elastic scattering on non-extremal black holes without charge, and they were thermal black holes, and they extracted the structure functions for these black holes. So in this work, what we are going to do is we are going to look at charged black holes, and we are going to look at the extremal region. That means where the temperature is 0. So so we are going to consider deep elastic scattering on large nucleus this extremal RNA-ADS black hole. So it has this geometry. So RNA charged black holes has 2 radius, one corresponds to the charge, and the extremal regime is when R plus is equal to R minus, and that gives you 0 temperature black hole called extremal black holes. And so we are basically conjecturing that these extremal black holes can be identified as a nuclei, and we are once we also include the fermionic fluctuations around the black hole, the Hawking radiation around the black hole, which gives you fermionic excitations around this black hole. Once you have that, the whole thing can be represented by can be understood as a nuclei.
What's the atomic number of this black hole nucleus?
So we'll normalize it and I'll show you.
Normalize it.
So this is the equation of state for this black hole, the extremal black hole. So unfortunately, at 0 temperature, these extremal black holes have finite entropy, which is order of NC squared, and the energy density is given by, so N is number density. So we are going to this black hole is defined for the volume is not it's just infinite volume. That means we don't have the finite volume effect on the black hole, but nevertheless we just assume we have this black hole in some volume given by this radius, and we'll identify the number density of these black holes by atomic number divided by the volume, which is N. Then we'll identify the energy by the energy of the black hole divided by its volume, and that gives out the energy per density, the energy per particle. That's the ratio between these two guys, and give you 3/4 mu. So that will be the energy
So it's a
per
nuclear matter
particle.
approximation. Infinite intranuclear matter.
And what is mu?
Chemical.
It's the chemical potential.
There's no variance.
Sure.
Yeah.
Oh,
So the baryons are going to show up as fermionic fluctuations, the Hawking radiation around the black hole, and we'll do one loop correction to whatever we're doing here.
Their fluctuations on average are variant is 0.
No, so this Hawking radiation itself has its own equation of state. In the presence of black hole, you have finite chemical potential. So you have this one loop in ADS that gives you the equation state for these fermion excitations. So this black hole is nothing but it's like a medium on which you have these fermionic excitations. And it's only once you put the fermions in that it looks like more like nuclei. But in large NC limit, you have this feature. It's like a medium, a nuclear medium on which you have these fermionic excitations. So at leading orders, the medium itself, the nuclear medium itself, or the extremal black hole on which there are these fermionic excitations, the background itself will have some structure function simply because it's still a black hole, and a black hole have dissipative part because of the boundary condition you impose near the black hole, which is you have to impose that there have to be incoming purely incoming boundary condition at the black hole. So that kind of boundary condition gives you dissipative part for the black hole, and that gives you structure function for the black hole itself. So then solving Maxwell's Fish. So our Bjorkan X will be defined as at set. So it's all the work we're doing here is similar to what they did for the thermal black hole. But here we will identify the Bjorkan X by in the rest frame. It's just the energy of this is just the energy of the nuclei, and we'll identify F1 and F2 from the imaginary part of the retarded Green function for JJ correlator. So as I told you earlier, so at leading order we are doing DIS on the black hole, and that gives you the structure function for the background. But this is 1 over NC squared suppressed, but it has its own effect, which is you have this Hawking radiation around it. You have a fermion loop, then you are scattering. You are doing deep elastic scattering on these fermionic excitations. So this is a one loop calculation, and in the presence of black hole. So we are almost finished doing that. We have the draft, so it will appear next week or something. But now my focus is on this one.
Ask whether this is fixed target situation or is it a fixed target situation?
It's a fixed target, yes. We are looking at the nuclei in this rest frame, and we're doing the ISO.
But it's known that we can boost black hole solution.
Yeah, you can do that, and you get some more complicated things, yes. So this is only in the rest frame, but you can boost it, and you can do GIS on the boosted black hole, and say, yeah.
Would it be worthwhile considering that?
Yeah. Yeah, that would be more interesting. But now we are looking at this one loop contribution. So at leading order, the structure function for the black hole. So we are going to look at very high energy scattering on the black hole. That means we can approximate, we can solve the Maxwell's equation in the presence of black hole near the boundary. So that simplifies the equations a lot. So from that, that corresponds to the small x regime of the structure function of the black hole. So this basically what we do. This is standard array safety calculation. So the effective action has this imaginary part, and we are after this imaginary part. So that second derivative will give you the green functions. So extracting the transverse and longitudinal structure functions is given by this. And also it's just like the thermal black holes, they satisfy approximate Callan-Gross relationship like this, F2 and F1. This is because the longitudinal part is, for small x, is very small. Also, the coefficient is also very small compared to the transverse one. So these alphas are some parameters basically because to get RN ADS black holes, you can use R-charged black holes, or you can also introduce disable branes, and in the low energy limit, the Maxwell's action will have some other coefficient here, depending on the flavor and stuff like that. But otherwise, it's very general.
Sorry, so EA is the energy, it's not the collision energy, right?
Yeah, EA is the energy of the nuclei.
The nucleus itself.
Yes.
Okay.
It's like
so,
8 times the mass.
So X dependence is really just X squared. So the 2/3 for FT, so to say.
Yeah.
Transverse term. So is it small X or large X?
This is a small x. Yeah, x upon.
So it goes to 0 very, very fast.
Yeah.
And FL really drops.
Yeah.
Like X.
Yeah. So this is basically what they found for the thermal black hole. So the only difference is the temperature is now chemical potential, stuff like that. And we have different identification.
So you have no works.
So
no X, for instance, right? Because you have 2 goes to 0.
yeah, so this corresponds to some kind of partonic distribution of, it gives you some partonic distribution of the black hole.
yeah, like a very counterintuitive from the
Yeah.
experimental standpoint.
Yeah.
Let's say. I mean, F2 doesn't go to 0. As X goes to 0, it's more the other way around. Because
Yeah. For you mean for what?
F2 proton.
Okay,
F2
well, yeah,
nucleus probably.
Yeah. Yeah. It's different for the proton. It's a different state, right?
Well, but again, from what we know from GIS and nucleus, okay, they kind of before AC, right? We haven't had very small X in the nucleus, but I think it's still very similar. I don't remember. Does anyone remember what F2 looks like for a nucleus?
It's the same as for a proton.
Yeah.
Shadowing is a shadowing effect, it's not
20%
gigantic,
or something,
right?
Yeah, so it should hold.
Yeah. So yeah.
I'm just saying that.
Yeah. It could be, yes.
Yeah.
So our interest is just to look at this structure function for the black hole and compare it with the structure function for the proton, which we already have from Porcini-Scaling structure. So now we'll compare the R ratio between this extremal black hole and the DIS on a nucleus. And we do some normalization here. So for the volume, and that introduces, so then this X will be just X for the rest. And we can write the saturation like this.
Saturation.
Yeah. So this is the ratio between the black hole and for the nucleon.
So how do you find saturation there?
It's just because since this is a small, it's only valid for small x for x less than the saturation scale. So if you write it this guy as, so xa square over xs. So this guy defines you saturation scale.
And how do you define saturation? How do you know that?
Because
by the block.
Yeah, you see, my remembrance of this is that the structure function is really zero until you get down to a very small x, and then it jumps.
In ATS.
Yeah.
It jumps to that.
yeah, that's the transition.
Yeah, you see, and that's got a very physical picture. I think this appears already in Chelsea. You know, imagine just starting out in QCD, and you've got start thinking an increment frame of a proton or a nucleus. Now you increase the coupling. Well, things cascade to smaller and smaller x as you increase the coupling. So you look at what's the deep inelastic structure function at x equals 1/3. And strong coupling is 0. There's no protons.
It's all gone.
It's all gone. And then it's gone. Until you finally get down to some small x, and they're all there.
But this is not terribly large either. If it's a very small x, it's all positive powers of x. I would have expected some sort of one of x. No, not in the situation. I mean, this also drops like a rock when it's
Yeah, that should be compared to the structure function at saturation, which grows like Q squared. And
you mean perturbations?
yes.
QS. Well, log cube of 1 over x. F2 goes as log cube of 1 over x.
Yeah.
So it still grows. It doesn't grow. So it's perturbative.
Yeah.
Okay.
So this is for the black hole. So this is like we are taking it like some medium on which we have this actual fermionic excitations. So looking at this R ratio between the black hole and each nucleon, this is how the ratio looks like.
Is this ratio meaningful in this discussion? If you treat proton and use differently, I mean, why not just discuss the nucleus separately?
Then you'll see something that's not very realistic.
So what's the point of this ratio?
Well, he's going to talk about shadowing here.
Right, but if you, is it really shadowing if the
You
small
can't
x-
talk about shadowing without knowing what the proton is.
Yes, of course, but the description of the proton and the nucleus are completely different in this.
Well, but he's
Cook it
saying
up.
that he's going to tell us
You
here.
always cook
He's
up,
going to tell us here that it's 0.85 at some small x. So it's not just completely different, it's 0.85.
I'm going to say
Because
It's right there. It's right there.
the ratio of two incorrect
No, but this
points.
No, wait,
the point
wait,
is not to compare to data, right? It's not, you're not comparing to data.
Why not?
Yeah,
Well, that's,
We have-
that's a pretty good number for the data.
Well, but again, I mean, the F2 is not going the opposite way. I mean,
So many years ago, I Kirill Fish and myself had this paper on elliptic flow coming from just two particle relations, and the ratio, which is elliptic flow, was wonderful. It was nice for the data. Each the numerator and
Was
denominator
1,000 off or something.
were like 1 over kt to
Exactly.
the fourth instead of 1 over kt to
So
the
ratios are misleading.
Yeah.
I mean, the ratios are misleading if you don't.
So this is yeah.
Illustrating your point.
So this is we're looking at the ratio between the nuclei and the black hole is our background. So we have the fermionic excitations. So they also have their own structure function. So we should look at the sum of this contribution and those excitations and divide by the proton. That's our final answer. So this is like a medium on which you have these fermionic excitations. But the medium itself has this kind of structure. So the dash curve is from holography. The solid lines are from this data.
So what A is this?
A is the same. I forget. Maybe it's 12%. Yeah.
No, but this is R,
Huh?
right?
This
So
is the ratio.
R. So this ratio of some A to the proton. So what's the A?
A is fixed.
So what? How large?
Yeah.
Like,
No. It's similar to what we have here.
oh, is it gold?
I think it's 12
Okay,
and
so-
45. It's not gold.
It's like 42 or
All right,
something.
so let's play another game. Let's take the ratio of different A's.
Yeah. What's the calcium to carbon
Well, the
ratio?
trend there was
it's
already wrong,
always shadowing.
right? The trend was
Always
wrong.
have the shadowing.
All right, so then maybe
Okay, so why is there 4 curves and 2 A's? Oh, you again have the data which is a solid. Wait,
Yeah.
solid curves. There are 3 solid
it's data.
curves.
Yeah. The solid lines, the 3 solid lines are for the data.
That's
So
why
the different nuclei numbers.
What?
There are different nuclei numbers.
3 different.
Yeah.
So okay, and the third one is some other number, and the other 2 are 12 and 42.
Yeah.
It's what
No.
it was.
I have to look up for the exact A's.
Okay.
Yeah.
Right, and you compare it to 1 dash curve. Shouldn't you produce 3 then?
Yeah. We should also produce a string. There's no
So what
problem.
should we compare your dash curve with?
Well, the trend is
Yeah.
all, the trend is not
No,
the same. Right?
Yeah. The point is the trend is the same. So when you look at the structure function of the black hole compared to the nucleon, have this kind of trend, and it's shadowing. That's the main point.
So the A is A decreasing. What's the trend from the blue?
Well, in
Which
the,
curve is the smaller?
in the data, the large A should be the green. The medium.
Right. Shadowing is increasing.
Wait. Actually, for the holographic part, the A dependence actually cancel out because once you have the structure functions, they are
You
linearly
said the A
dependent.
cancels out.
Yeah. So when you divide by the
Oh,
A
it's
times
just
the proton,
linear and
it's
A.
it's
But
independent.
then
of
your ratio is 1. The ratio should be 1. The shadowing ratio.
No. This is A times whatever you have. That's for the nucleus.
This is only for nucleus.
This is the nucleus.
So protons are different. So
Protons are
protons are not the A equals 1 limit of this formula. Protons are something completely else.
Yeah.
Oh, I see. So,
But if you take nucleus to nucleus ratios,
That is V1.
It's just
Yeah.
one.
It is calculated one.
So this A naturally comes there, and you are dividing it A times for the
which is 1
It's like A.
nucleus.
It's like A dot infinity.
right, it's
He's doing internuclear matter. It was surprised if he's doing that A dependence, right?
Yeah, because we don't have volume effect. We're assuming just. Okay. So this is what it is. So this, as I say, this will be more realistic once you include the fermion loop, which corresponds to baryonic fluctuations in the nuclei. So that is ongoing work, and it will be reported next week or so.
just to ask about numbers, as people said, is getting 0.85 is quite surprising. Thinking that these two approaches are quite different. One is the purely particle approach, and the other is the lateral approach. Did you have any parameters you have chosen to actually get the numbers, or it just comes out naturally?
No, it just comes naturally.
Just a natural.
Yeah. There's,
coefficient.
yeah. All the coefficients comes natural.
That seems somewhat non-trivial.
Yeah. It's just the characteristics of the black hole. We are not doing anything to it. Okay. So we have. So this is the summary and the conclusion. So we have used they are scattering on a single nucleon to make number one estimate of the nuclear structure function for the dilute nuclei. And we have found that the radiation contribution is on one nucleon smeared by its Fermi motion, and it compares well with data for large X. We have described also a dense nuclei as RNA, extremal RNA-dense black hole. And from the R-current correlator, we have determined the structure function and found that it exhibits some shadowing at low X. So this is the conclusion. Thank you.
So, questions?
So your curves go down to x equal to 0, and they remain finite there, or is there a singularity?
No, they go to X. They go to X0.
That's what I mean. So it's because it's a fractional power. That's why it
Yeah,
curves.
yeah. Because the black hole is x to the power of positive coefficient, and the graviton exchange is 1 over x to the power of negative power. So the result is the ratio is x to the power of positive power. In such a way that
the ratio goes to 0.
Yes.
But I didn't. Could you show the plot again?
We just cut it off, and so he didn't go for
Yeah.
Oh, so it will drop down to 0 eventually.
Yeah. It will go to 0.
Really cool.
Qualitatively.
Looks like it's zero.
Yeah.
No, it's
there it is,
No,
right
it's-
there. See the ratio is 2x.
It's close to a constant. There's some constant coming from. I'm not sure here.
but it was the ratio.
You had the ratio there a moment ago.
Yeah.
Wait,
Right,
Yeah,
right,
this
right.
one.
The x is right.
So what's delta P again? 2?
The delta P is it's 0.08 or something. It's 1 minus
Oh, yeah,
1 over lambda correction.
And you pick the lambda just right to get 0.08.
No, it's actually as long as this alpha P is a positive number, you always get this, and it's always positive.
That's what I'm saying. Yeah. Shouldn't
No, it doesn't go to 0 because of this normalization we have. So because
Is this the formula you had for R? Is this the formula that you are talking in the plot?
yeah,
This formula.
this is what it is.
So C tilde T, C delta XS are all constants.
Yeah,
And then delta P is larger than minus 1/3.
yeah.
So then it goes to 0, right?
Well, it depends on what is delta.
No, it depends on what delta P.
No, but XS
is constant.
Yeah, it's
Oh, X. I'm sorry. XS isn't an X.
Yes,
Very
I
good.
also
very
was
good,
looking at
very
it as X.
Very good.
yeah,
So long as delta P is positive. it's gonna be
yeah.
zero,
This guy's cancelled. It's going to be a constant here.
No,
That's what you
right, in the front.
Yeah.
You have a factor of X.
Yeah. So
Okay.
this guy comes here, and it will be constant. But
Oh, you
then
mean
it
that
is just
is like
X.
a lower bound? Or?
Yeah. So it goes like this. So this term has X dependence. This guy is cancelled because of this exponent in such a way that they cancel. So you have a constant.
Oh, I see. The second term goes to a constant, you said.
So
Yeah,
so delta P is minus
Because if yeah.
So delta P is minus 1/3.
Ah,
No, then the whole thing would explode.
delta P must be.
Delta P is
must-
minus 1/3?
No, it's
No,
not.
sorry.
minus
Delta P is-
minus one.
Minus
cancel
1/3.
has to be minus.
If it's minus 1, then the
Yeah,
first term goes
It's
up.
two minus one. Yeah.
Yeah, delta P. So delta P is minus 1. Is that?
No, but then the first term would be singular.
Then the first term explodes.
Yeah.
You
It's,
get 0.85.
Yeah,
So when you take x equals 0, and in the bracket, the second term is small. The second term is 0 compared to the 1. So x equals 1, you just take 1.
Yeah.
And then either it goes up or it goes to 0. There's no.
No, it goes to a constant because of
So
this.
delta p is minus 1/3 then?
How can it go to a constant?
So what's the value of delta p?
So yeah, I have it on the paper, but I don't. It's like 0.08 or so.
It goes to 0.
Okay, so then it goes to 0.
The only possible number is minus 1.
The only possible number is 0.08 because that's the right number. Right? Also known as 1/4 pi.
Go to a constant.
Okay, good.
I see.
Okay.
I think good.
What time do we start tomorrow?
9:30.
What time do we start?
At 9:30, right?
Or should we start at 9 to accommodate? Oh,
And do we want to start at 9 to have more time for discussion, or
We have 2 talks tomorrow morning? Is that-
yes.
2 o'clock tomorrow morning?
1 in the afternoon.
No time today, but
Today was this day.
Today was okay because we had the buffer. We
Even
actually
though,
went past
even though
both.
We had a
everyone-
buffer last
Oh,
the
the
second
second
talk didn't go over
50%
time.
overboard.
Everyone went over time, but the second talk did not go.
Yeah, but we did leave the room after talk to myself.
Yeah.
Tomorrow we must leave the room at 12.
Yes.
Yeah,
we
so
can-
let's start at
but
9.
we can
Let's
make it
start at
some-
9.
There is something
So
after.
it's-
So you should start at 9.
So we should
It's about a
start at
coffee break.
Yeah. Okay, if you guys could ask Cheryl.
You asked for this time. You changed it.
If everybody's here, we don't need to.
Well, just in case, I think it's better to.
No comment.
No
comment.
Yeah, okay. Everybody, yes, like the Barbara's not here.